So if your question is to perform hypothesis test for some sample statistic, for example, some sample mean, then you don't need hypothesis test, yeah, because you already know the exact value of a statistic for sample, ya. Jadi uji hipotesis maupun perhitungan selang keyakinan, ya, singkatnya adalah inferensi statistik. Ini selalu kita lakukan terhadap parameter populasi. Kita tidak pernah melakukannya terhadap statistik sampel. Kenapa? Karena kita sudah mengetahui secara eksak nilai-nilai penciri sampel tersebut, ya. Oke, ini supaya kalian nggak bingung ya. Jadi uji hipotesis maupun perhitungan selang keyakinan itu selalu dikenakan terhadap parameter populasi. Rata-rata populasi kah, varians populasi, apapun itu. Same as here that we discussed today. So when we say two sample hypothesis test, what we're testing for is not exactly those samples, but the population from which those sample originates. Ya. Jadi kalau kita mengatakan, oke, saya melakukan uji hipotesis 2 sampel, ya, yang diuji itu bukan sampelnya. Sampel adalah sarana untuk menguji, yang diuji adalah populasinya. Ya. Kenapa? Kalau kita terfokus pada sampel itu kita tahu secara eksak besaran pencirinya. Okay, so pay close attention. We always know the exact value of sample statistics. Rata-rata sampel, varian sampel, simpangan baku sampel, itu semuanya kita tahu secara eksak. Gitu. Yang kita nggak tahu adalah penciri populasinya. Dari mana sampel tadi berasal. Makanya kita perlu prosedur-prosedur inferensi ini. Baik itu prosedur perhitungan selang keyakinan maupun prosedur uji hipotesis. Yeah. So the problem is always the population parameter, which we never ever know the exact value of. Okay. So this is an easy example to imagine. Okay, so let's say that we are asked to compare the performance of these two machines. Okay, so these are emulsifying mixers to make creamy cosmetics production. Okay, like what do you call it? Skincare products. Okay, anything that has the consistency of a emulsion or paste or cream. Okay. So let's say that we have two machines working in our production floor. Ya, jadi misalkan ini ada 2 mesin pencampur emulsi, ya, emulsifier, yang memproduksi produk perawatan kulit atau perawatan kecantikan. Oke, krim, kemudian apapun ya, produk-produk yang berupa krim atau pasta. Ya. Nah, karena ini adalah produksi di skala industri, maka konsistensi antara mesin A dan mesin B itu menjadi penting. Ya. So because we're talking about industrial level production, okay, industrial level quality control, then we need to make sure that machine A and machine B works consistently against each other, meaning we cannot differentiate the product produced by machine A and machine B. So in other words, when we need to confirm if machine A and machine B are equivalent, okay, in terms of product viscosity, right? Now remember, this is only examining just one product parameter, which is the product viscosity. Of course, in an actual product, you have many other things that you need to consider, okay, aside from viscosity. Skin feel, shelf life, and many other parameters. Here, for our discussion, we only focus on one product parameter, which is the product viscosity. Okay, so when we want to say if machine A and machine B produces the same viscosity, yeah, what must be done to answer that question? Okay, let's assume that this is the distribution of the product viscosity produced by machine A, and this is the distribution of product viscosity produced by machine B. So when we want to confirm whether machine A and machine B works similarly to one another, then how can we say that? What must be equal between machine A and machine B to confirm that these two machines works similarly. Ya, jadi kalau kita ingin mengatakan apakah mesin A dan mesin B ini cara kerjanya sama, maaf, kinerjanya sama, ya, apa yang harus kita cek? Go back to your descriptive statistics. Two sets of data are equal if and only if what? Coba kembali lagi ke statistika deskriptif, ya. Gimana? Ada yang bisa menjawab? So when can we say that two sets of data are statistically identical? Go back to your CV dot. Go back to your descriptive statistics or data descriptors. I think this is one of the module 1 exam question, I think. Can anyone guess? Is anyone awake? Okay, turn on your cameras, please. Okay, I want to check if you guys are even there. Yeah. Okay. Can just guess? I'm not. This has no grades attached to it. So can anybody guess if we want to say that two sets of data are identical to each other, then how should they behave in terms of their descriptors, data descriptors?
Sir,
Yep.
Is it when they have similar variance and mean?
Yes, and more. You're right. But you need if we want to say that those two sets of data are absolutely similar in all aspects to each other, then not only means and variance, but also the shape of the distribution, okay, the presence or lack thereof, or lack of outliers, and also how they behave with time, okay. Now, in most cases, you're right, okay, in most cases, it is sufficient to say that their means and their variances are equal to each other, because normally we assume that those two data sets are, they behave or they are distributed according to normal distribution. Ya, jadi memang dalam banyak situasi kita sering mengasumsikan pertama kali, data A dan data B ini terdistribusi secara normal. Ya, itu asumsi yang implisit. Kenapa? Karena biasa dalam banyak sistem yang kita pelajari di teknik kimia memang betul rata-rata kebanyakan mereka mengikuti distribusi normal. Ya. Oke, jadi setelah asumsi itu diambil, kemudian untuk kita bisa mengatakan apakah mesin A dan mesin B ini kinerjanya sama, maka ukuran pusat dan ukuran sebaran dari output kedua mesin itu harus identical. So they have to be statistically not different, okay, in terms of means and in terms of variance or standard deviation. Now, in some cases, we are interested in only one of those dimensions. Okay. Now, you answered that. So your answer is quite complete in the sense that it has included measure of central tendency and measure of spread. Ya, jadi jawaban kalian tadi sudah mencakup ukuran pusat dan ukuran sebaran. Nah, tergantung dari kasus yang kita hadapi, bisa jadi kita hanya berkepentingan menguji salah satu di antara kedua itu. Okay, so as we have discussed last week, when we test equality of means, then it implies that we are only interested in the measure of central tendency. Conversely, if we are doing a hypothesis test on variance only, then it implies that we are only interested in testing equality of measure of spread. In some cases, we need both. Ya, jadi tergantung apa yang ingin kita uji. Apakah kita sedang berkepentingan atau sedang ditugaskan untuk menguji rata-rata alias ukuran pusat, atau kita sedang berkepentingan atau kita disuruh menguji kesetaraan varians. Ya, kita menguji ukuran sebaran. Kadangkala kita memang memerlukan dua-duanya, kita memang perlu menguji dua-duanya. Jadi ini tergantung dari what we want to prove. Ya. Okay. So our focus for now is testing the equality of variance. Ya, jadi yang kita uji sekarang adalah uji kesetaraan varians, alias dengan kata lain uji kesetaraan ukuran sebaran data. Okay. With the assumption that the two data that we're comparing are both normally distributed. Okay, so this is an important, this is a key assumption. Whoops, sorry, I don't mean to strike that. Okay, let's erase that. There you go. Yeah. So, okay, it only means that in order for the subsequent calculations to be valid, then the population, the original population from which the data or the samples were taken, they have to be normally distributed. Ya, jadi ini asumsi yang implisit bahwa populasi induk, ya, yang kita tempat asal sampel itu kita ambil itu harus terdistribusi secara normal. Maksudnya apa? Kalau nggak normal, rumus-rumus yang kita pelajari di bawahnya ini nggak valid. Itu aja sih sebetulnya. Ya. Okay, and the figure on the right-hand side here, this illustrates the situation that we're dealing with. So we're dealing with two data sets, okay, one in blue and one in green, yeah. And we want to check whether these two data sets have different variance, yeah. Of course, if you just take a look at it at the data, you can perhaps guess that these two data have different variance. But again, a guess is just a guess. It's not valid until you do a quantitative test, ya. Jadi dalam uji yang kita pelajari sekarang, kita ingin memastikan apakah varians atau sebaran, ya, sebaran dari kedua data ini. Okay, so this is the first data set, and this is the second one, ya. Jadi data setnya ada yang digambar dengan warna biru dan hijau. Kita akan memeriksa nih, apakah sebaran dari dua data ini berbeda atau enggak. Nah, kalau kalian lihat dengan mata, ya oke lah, mungkin kelihatan memang yang data yang hijau ini sebarannya lebih lebar daripada yang biru gitu ya. Tetapi itu hanya sekedar tebakan kualitatif saja. Tidak ada artinya sebelum kita melakukan uji kuantitatif. Ya. Oke, pernyataan hipotesisnya seperti begini. Okay, so this is the general way to set up the hypothesis statements. So the null hypothesis is like this. Okay, variance of population A is equal to variance of population B. Now, again, pay close attention here. This might sound small, but this is actually quite important. We always test we always test population parameter. We never test sample statistics. Oke, jadi kita uji, kalau kalian lihat ya, yang kita uji di sini adalah parameter populasi, bukan statistik sampel. Kita nggak menulisnya kayak gini. Nah, we never ever write it down like this. Okay, so this is variance of sample A. Is it equal to variance of sample B? So we never do it this way. Okay, we don't need hypothesis test for a sample. Again, because we already know for exact the value of sample variance. It is the value of population variance that we don't know. Ya, jadi kita tidak pernah menulis H0 itu seperti yang saya coret ini. Nggak perlu, ya, karena kita sudah tahu secara eksak berapa nilai varians sampel. Ya, jadi kalau kita tulisnya dengan huruf Latin S kuadrat A alih-alih sigma kuadrat A, itu maksudnya adalah varians sampel, bukan populasi. Ya, beda ya. Nah, kalau kita bicara sampel, kita nggak perlu uji hipotesis, karena kita sudah tahu exactly berapa nilai varian sampel. Nah, masalahnya kan sampel ini kita ambil dari populasi, ya kan? Dan yang ingin kita tes itu bukan sampelnya, sampel itu perwakilan. Yang ingin kita tes adalah populasi yang ada di belakangnya tuh, ya. Okay, so we never ever write down hypothesis like this. Okay, so this is the wrong way of writing our hypothesis. Okay, it's philosophically incorrect and therefore mathematically incorrect as well. Okay, yeah, so let me erase that. There we go. Yeah. So the null hypothesis is always written down like this. Okay, variance of population A equals variance of population B, and then the alternative hypothesis can be like this. Okay, so it could be written down as variance of population A less than B, or variance of population A more than B, or variance of population A not equal to B. Okay, this would be, the first two would be a one-tailed test, and this is a two-tailed test. And because the test statistic is called the variable f0, then we call this test f test. Yeah. Okay. And it has been found if we calculate this quantity, ya. Jadi kalau kita menghitung, ya, kalau kita menghitung varians A dibagi varians B, di mana populasi A dan populasi B dua-duanya terdistribusi secara normal, okay, then the ratio of variance of those two samples, so of those two populations, sorry, I get confused from time to time as well. Okay, so the number is called F, and this F number follows the F distribution, yeah, which looks something like this. Okay, so this is the F, so this is the distribution of the random variable F, ya. Jadi ini adalah distribusi probabilitas dari bilangan acak F, bentuknya kayak gini, ya. Ya, oke. Saya kembali lagi ke slide sebelumnya. Jadi kalau kita menghitung, ya, kalau kita menghitung nisbah atau perbandingan antara dua buah varians, ya, dan populasi asal dari varians A dan populasi asal dari sampel A dan sampel B ini dua-duanya terdistribusi secara normal, maka varians cuplikan and thereby varians populasi, kalau kita ambil rasionya, rasio tadi akan mengikuti distribusi F, ya. Sehingga besaran rasio tadi kita beri nama F0, ya. Oke. Again, let me repeat it from another way, from another approach. Okay, so F0 is defined like this. So F0 is the ratio of variance, okay, of the two data sets, yeah, in which the numerator variance is always chosen to be the greater one. Okay, so if you have two data sets with different variances, common practice is to set the numerator to be the bigger one and the denominator to be the lesser one, the smaller one. Ya, jadi kalau kita membandingkan dua buah varians, maka varians yang lebih besar itu by convention selalu dipasang sebagai pembilang, dan varians yang lebih kecil dipasang sebagai penyebut. Oke, ya, jadi pembilang lebih besar, penyebut lebih kecil. Karena itu, because we always set the larger variance to be the numerator and the smaller one to be the denominator, then F0 automatically becomes always greater to or equal than 1. It is never less than 1. Yeah. So automatically F test, sorry, this should be written automatically, okay, not the automatic. So automatically F test is always a one-sided right tail test. Yeah. Okay, because again, let me write down here. F test is the one that is, I think this is the most confusing test among all of the hypothesis testing because of this requirement. Okay, so let's see this one here. Okay, so previously we have H0 is like this, right? Now let us assume that, sorry, not that one. Race. Now let us assume that variance of A is variance of sample A. Now remember, okay, variance of sample A is larger than, this is not a good way of discussing it. Yeah, anyway, okay. Now pay close attention to this one. What I'm writing down here is the sample variance, not the population variance, okay? So this will be the value, whatever value that you're observing from your experiment, from your measurement, okay? So because from your measurement, variance of sample A is larger than B, then the F0 will be okay, because this is larger. Okay, so larger variance always goes on top, smaller one always goes to the bottom. So therefore, if we state our H0 in terms of F0, then F0 will always be equal to or greater than 1.0, right? If variance of population A is exactly the same as variance of population B, then the F0 will be 1, okay? And if either one of those variants is greater than the other, and because we require that the bigger one is put on top and the smaller one is put on the bottom, then the F0 will be larger than 1. So there are only two possible situations of F0. Either it's equal to exactly 1 or larger than 1. Okay. In other words, the F test will automatically become a one-sided right tail test. Okay. Okay. And then we obtain the critical F value, okay, from F table as a function of alpha, okay, significance level, the usual. And we now have two sets of degrees of freedom. We have two quantities of degrees of freedom. Okay, this one is, we call this one the numerator degree of freedom. Okay, derajat kebebasan pembilang. This one is the denominator degree of freedom. Ya, derajat kebebasan penyebut. Ya, supaya nggak bingung, jadi kita tetapkan saja ada indeks A atau indeks 1 itu maksudnya adalah pembilang, dan B atau 2 itu adalah penyebut. Ya. Varians pembilang lebih besar daripada varians penyebut. Okay. And this is the F table. You know. It's quite clearly marked here, actually. So the first column, this is the denominator degree of freedom. Ya, jadi ini adalah derajat kebebasan penyebut. Nu2. So the symbol is Nu2. This is the Greek letter Nu. Nu2. And the top row here, ya, the top row here designates the numerator degree of freedom. Jadi ini adalah derajat kebebasan pembilang, ya, diberi simbol huruf Yunani Nu1, Nu1. Okay, right? And the numbers inside the table, this is not the probability. This is the value of the F, of the critical F value that corresponds to the situation here. Okay, so this one table, this entire table here is actually only for one value of alpha. Ya, jadi derajat kebebasan yang jadi satu tabel ini mengacu pada satu nilai probabilitas, yaitu 5%. Ya, kalau kalian lihat di buku, kalian akan menemukan tabel yang serupa untuk alfa yang lain, untuk alfa 0,1, kemudian untuk alfa 0,01. Oke. So each value of alpha have their own set of table. Okay. Now, anybody not clear yet about how to read F table? Again, let me repeat it this more slowly. Okay. So the value of alpha is unique for each table. Ya. Jadi setiap tabel itu berkorespondensi dengan satu nilai alfa. Contoh yang saya tampilkan di sini, ini adalah tabel untuk alfa 5% saja. If you need a different value of alpha, then you need a different set of table, which you can clearly, you can easily identify or you can easily look up in your textbook. Okay. And again, on the top row here, di baris yang paling atas, this is the degree of freedoms for the numerator, for new one. Okay, so we have degree of freedom of 1, 2, 3, 4, 5, 6, and so on. Yeah. And the left-hand most column, this is the degree of freedom of the denominator, new 2. Ya. Jadi ini derajat kebebasan penyebut. Derajat kebebasan penyebutnya ada 1, 2, 3, 4, dan seterusnya. Okay. So for example, we are asked to find, okay, let me just give you an easy example here. So let's say that what is the value of f at alpha of 0.05, okay, and new one of, let's pick a random number, new one of 5, ya, jadi derajat kebebasan pembilangnya adalah 5, and new 2 of 10, ya. Jadi misalkan derajat kebebasan pembilangnya adalah 5 dan derajat kebebasan penyebutnya adalah 10. Okay, so again, this one is of course the alpha, this one is new one, okay, derajat kebebasan pembilang, dan ini adalah derajat kebebasan penyebut. Yep, oops, sorry about that. Oh, come on. It's getting close to the edge there. That's okay, yeah. So what is the f value that corresponds to those settings? Yeah. Of course, because this is a table. This is the table for alpha equals to. Where is my pen, by the way? Oh, yeah. Okay. So this is the table for alpha equals to 5%. So clearly we are on the right table. We are on the correct table. Yeah. And let's take a look at where new one equals to 5 is. So this would be this one here, right? So this column is for new one equals to 5. And then which row corresponds to new 2 equals to 10 is this one, right? So all we have to do is to find the intersection, which is this one. Okay. So this would be f at alpha equals to at alpha equals to 0.05, right? And then first degree of freedom is 5, new one is 5, and new 2 is 10, equals to 3.33. Okay, easy, right? So of course you need to pay attention to how we define the F table. So again, F table is defined as this one-sided right tail distribution. Okay, one-sided right tail distribution. Yeah. Okay, so let's take a look at this one example here. Yeah. Yep. So these are actual numbers actually. Okay, so these numbers are real numbers. They were measured by. Okay. So these are measurement results from 2 years ago, I believe. So your adik angkatan, okay, they performed these measurements. So I asked them to measure the mass, okay, the mass of Caca candies from 2 packages. We did this in class, so this was before the pandemic, okay. Jadi 2 tahun yang lalu saya membawa 2 bungkus permen Caca ini ke kelas, ya. Dan kemudian saya minta mahasiswa saya untuk secara bergilir mengukur berat setiap butir permen Caca dari 2 bungkus tadi. Okay. Package number 1 is bungkus number 1 and package number 2 means bungkus number 2. Yeah. And package number 1 contains 27 pieces of candy and package number 2 contains 30 pieces of candy. Yeah. And this is the average mass, the average weight of one candy in package number 1, 1.29, and this is the average weight of candy from package number 2, 1.25. And these are the sample variances. Okay. So at 95% confidence level, prove the consistency of mass variance per grain chocolate per piece of candy. Geez. Okay, in the 2 packages. Sorry, I'm not the one who made this translation. Okay, sorry about that. All right, so what is the initial claim? The initial claim is that the variance of mass per... Nggak enak bunyinya, sorry about that. So let me change this really quickly. Variance per, not grain chocolate, per piece of candy. There we go. There we go. There we go. So we are interested in comparing the variance, ya, sebaran antara berat per butir coklat di bungkus 1 dan bungkus 2. Okay. Yep. So the initial claim, the variance of mass per piece of candy of both packages are consistent, are the same, equal. Yeah. If the initial claim is wrong, the correct statement will be this one, right? And out of those 2 statements, of course, the first one contains similarity. Yeah. So the first one becomes H0 and the second one becomes H1. Yeah. The H0 is set up like this, and the H1 is contains inequality. Okay. Now let us start calculate the. Geez. Sorry about this, guys. I didn't have time to check the translation, so this should be test statistic. There we go. Yep, statistic uji. So that's the Indonesian term for it. Okay. So next, after we construct the hypothesis, we calculate the test statistic, which is called the F0. So F0 is larger variance divided by smaller variance, which results in the number of 1.043. Then we find the corresponding critical value of F, or critical F value, when alpha is 5%. And now, be careful with this, okay? Bu Vita and I had just a discussion this morning about how to interpret this one. So let us be a little bit more careful about this. And this one is actually have to be, so I'm putting the wrong value here. This should be F at 0.025. Okay. And at new one of 26. So the degree of freedom in this case is number of sample minus 1. So size of sample minus 1. Okay. This one is 29. Yeah. Cool. So this is actually wrong. Okay, this is actually incorrect. This should be try to find the value of f for an alpha of 2.5%. The reason why I'm changing the alpha from 5% to 2.5% is because the way we write down H1 is like this. Okay, so this originates from a two-tailed situation. Two-tailed. Ya, oke. Jadi ada hal yang harus dikoreksi dari diktat kita ini ya. Kalau kita lihat pernyataan hipotesis alternatifnya, ya, ini bunyinya adalah varians A tidak sama dengan varians B. Ya toh? Oke, bukan apa-apa karena memang kasusnya begitu ya. Jadi klaim awalnya yang dibuktikan adalah bahwa varians massa per butir permen antara bungkus 1 dan bungkus 2 itu sama. Oke. Itu yang klaim itu yang ingin dibuktikan. Klaim awalnya adalah varians A sama dengan varians B. Kalau klaim awal ini salah, maka yang menjadi benar adalah varians A tidak sama dengan varians B. Dalam kasus yang kita pelajari ini, kita tidak peduli apakah varians A lebih besar atau lebih kecil daripada B. Ya toh? Yang ingin kita buktikan adalah varians A tidak sama dengan varians B atau sama dengan varians B. Oke, maka originally ini adalah masalah uji dua sisi, two-tailed. Ya. Oke. Nah, dalam uji F ini memang agak membingungkan ya, karena uji F itu secara matematik ya hipotesisnya itu menjadi satu sisi, yaitu H0-nya. Kalau H0 ini dinyatakan dalam F0, kalau H1-nya dinyatakan dalam F0, otomatis dia menjadi uji satu sisi. Oke, like this one here. Ya. Because we always set the larger variance on top and the lower variance at the bottom, then this implies that mathematically F-test is always a one-sided right-tailed test. Because we don't, mathematically it is impossible to obtain a value of F0 less than 1. Right? It's always 1 or larger than 1. Yeah? However, because in the example, originally this was formulated as a two-tailed problem, ya. Jadi secara matematik kita sudah lihat bahwa uji F itu adalah uji satu sisi sebelah kanan. Karena cara kita mendefinisikan F0 adalah variansnya yang besar ditaruh di atas, yang kecil ditaruh di bawah. Jadi nggak mungkin kita mendapatkan nilai F0 kurang dari 1. Ya. Sekali saya ulangi ya. Secara matematik uji F otomatis adalah uji satu sisi sebelah kanan karena cara kita mendefinisikan F0 yang sedemikian sehingga memaksa itu. Tetapi kalau kita lihat contoh yang ada di layar sekarang, masalah ini awalnya dirumuskan sebagai masalah uji dua sisi, two-tailed. Ya kan? Karena kita tidak mementingkan apakah bungkus A variansnya lebih besar daripada bungkus B atau enggak. Yang kita ingin buktikan pokoknya beda apa enggak, itu aja. Kita nggak peduli mana yang lebih besar, mana yang lebih kecil. Ya. Jadi ini adalah masalah uji dua sisi sebetulnya. Nah, bagaimana ngakalinnya sekarang? Karena secara matematik definisi F0 itu sendiri adalah satu sisi, tetapi rumusan hipotesisnya ini harusnya dua sisi. Nah, jalan keluarnya adalah untuk masalah seperti demikian, ya, alfanya itu adalah tetap alfa dua sisi. Jadi alfanya dibagi dua. Karena kalau kita lihat distribusi F-nya sebetulnya daerah penolakannya ada dua. Untuk masalah kita ya, ini sekali lagi tolong diperhatikan untuk kasus kita ini, sebetulnya daerah penolakannya itu ada dua aslinya. Karena kita nggak peduli mana bungkus permen caca yang variasinya lebih gede. Kita nggak peduli apakah bungkus A lebih gede variasinya daripada bungkus B atau lebih kecil, pokoknya beda. Ya. Jadi daerah penolakannya sebetulnya ada dua. Karena daerah penolakannya ada dua, maka alfanya kita split jadi 2. Oke. Kiri dan kanan masing-masing besarnya adalah 0,025. Jadi angka yang saya tulis di sini ya, hati-hati, F0 yang saya tulis di sini 1,818 ini salah ya. Karena dia dihitung pada alfa 5%. Harusnya dia maaf, F kritik ini ya, ini 1,818 ini F kritiknya salah. Jadi kalian nanti coba cari ya. So I want you guys to find on your own, look at your textbook and find what is the correct value of critical F. Okay, it should be found at alpha 0.025, not 0.05. Okay. Okay, any questions so far? If not, let's take a 5-minute break. I also need to do something because I have to leave. Actually, I have to leave at exactly 9 to the campus because I have a critical meeting in the campus, offline meeting. Okay, so we need to be done at 9:50. Okay, so let's take a 5-minute break for now. I need to drink some water as well. Okay, as you can from my voice, it has already deteriorated. Okay, so I need to drink some water. Okay, let's take 5. Okay, take a 5-minute break. All right, let us continue. Now let's move on to the next segment. It is, there we go. Oh, no, this one. Stop presenting. What did I do? Okay. Yeah. There we go. Okay. So this is actually the last subtopic for statistical inference. Oh, wait. Yeah, okay. So we have come to the last part. So this is actually the last segment of our theoretical review of hypothesis test, which is the hypothesis testing of the mean of two samples, using two samples. All right, so let's take this situation for example. Okay, so we have two samples. Again, please make note the difference between sample and population. Okay, so now we have, let's assume that we have two samples. Okay, sample A and sample B. Sample A, the average, the sample mean of A is 17.5, and the standard deviation of sample A is 1.31. Okay, and as you can see, we assume that the original population from which sample A originates is normally distributed. Okay, and here this one is the brown one is sample B. So the sample mean of B is 19.7, and the standard deviation of sample B is 0.96, right? And if we only take a look at the sample, clearly we can see that the mean of sample A is less than sample B, right? So 17.5 is always less than 19.7. But again, that's not the point in statistics. What we want to prove is the population mean of A against population mean of B based on the data from sample A and sample B. Ya, ya jadi kalau yang ditanyakan adalah bagaimana rata-rata sampel A dan B, ya sudah jelas rata-rata sampel A itu lebih kecil daripada rata-rata sampel B. Ya kan, ini kan kelihatan angkanya 17,5 dan 19,7. Tapi poinnya bukan itu. Jadi inti dari persoalan adalah oke, bagaimana dengan rata-rata populasi A dan populasi B berdasarkan data sampel A dan data sampel B. Oke. So, however, is the mu sub A is the mean of population A, definitely less than mu sub B. Okay, so this is the key question. Okay, and we have to answer this question based on the data of sample A and sample B. Okay, so there's always uncertainty in the population mean measurement. There's always differences. There's always variation in our observation and our sampling. Okay, which implies that if we are to repeat this measurement many times, then we may end up with different values of means, of sample means and sample variance, right? And you can, one of the most important point in the video that we posted last week, you know, the old video jadul dari YouTube ya, yang dari Professor Stuart Hunter. One of the key points in that rather long video is that there's always variations in observation. There's always variation in sample means, in sample variance. Okay, so we can never ever be certain before we do a hypothesis test. We can never rely on just sample statistics to draw any conclusion. Sample statistic must represent population parameter. Yeah. Let me move this up a little bit because otherwise my face will cover it. Okay. There we go. That looks much better. Oh, don't want that, man. Yep, there we go. This one too, I think I need to move that a little bit to the top. Up there. There we go. Okay. Okay, let's get back to it. Yeah. All right. Now the general form for the hypothesis statement for the two samples mean test is as follows. So the null hypothesis is always written like this, okay? Mu sub A equals mu sub B, or alternatively, you can also check for specific difference between A and B. Okay, so you can also write down the null hypothesis as mu sub A minus mu sub B equals some difference, ya. Jadi yang namanya hipotesis nol itu tidak harus bunyinya seperti begini, ya. Bisa juga kita menguji, kita ingin memeriksa apakah ada selisih tertentu antara mu A dengan mu B, ya. Selisih tertentunya itu delta nol ini. Oke. Jadi misalkan kita ingin menguji ya apakah misalnya ya misal nah gini nih misalnya mungkin kalian pernah mendengar barangkali rumor-rumor gitu ya, dari tingkat itu ya, oh kalau ujian kompre yang bulan September itu lebih gampang soalnya, atau yang bulan Maret itu lebih gampang soalnya, jadi nilainya lebih bagus daripada yang kompre Juli misalkan begitu. Jadi kalian ingin ngetes nih bahwa ada selisih tertentu nilai ujian kompre yang bulan Juni ya, yang bulan Juni dengan yang bulan September. Dan selisihnya itu katakanlah misalkan 10 poin. Ya. Kalian menduga bahwa soal kompre, ujian kompre yang September itu nilainya selalu lebih bagus 10 poin daripada yang Juli. Okay. So let's say, for example, that you want to test the claim that comprehensive exam in our program, study program, in September period is always larger by some increment compared to the compared to the June exam. Let's say that you want to test the claim that students consistently score 10 points higher in the September exam compared to the June exam. Yeah, okay. Now, so if you set that number to be some definite increment, then you put that increment here, the delta zero. But if you want to test equality between sample A and sample B, then of course, the delta zero will be 0. And you will get this type of null hypothesis. Okay, mu sub A equals to mu sub B. Yeah. All right, and then these are the possible statements for the alternative hypothesis, right? Mu A less than mu B, or mu A larger than mu B, or mu A not equal to mu B, or if delta 0 is not 0, then the alternative hypothesis is written down like this: mu sub A minus mu sub B less than delta 0, or this would be the right-tailed version of it: mu sub A minus mu sub B greater than delta 0, and so on. Okay. Now, there are several cases of two samples mean hypothesis testing. Again, in this module, in this segment, we are interested in testing the means. We are interested in comparing the means of two populations based on two samples. Ya. Jadi kita membandingkan rata-rata dua populasi berdasarkan dua sampel yang diambil dari populasi tersebut. Okay, now what are those subcases. Ya, jadi subkasus apa saja yang ada di dalam uji hipotesis terhadap dua sampel ini. Oh, what did I do? Sorry about this. I'm still fiddling around with Microsoft Teams, so as you can see, I'm not an expert yet, and I'm not really sure how I end up in this display. Oh, okay, so we're back again. Okay, so the first one is two independent samples with known population standard deviation. Independent samples meaning that we don't have any correlation between sample A and sample B. Okay, take this for instance. Yeah, so you see on the left-hand side, the plant is fertilized, and the right-hand side, the plants are unfertilized. So, and of course, the identity, the individual identity of the plants are different, right? So this is plant number 1, that's plant number 2, this is perhaps plant number 3, plant number 4. So these are individually different species, it's individually different plants. So we say that the member of population A doesn't have anything to do with the member of population B. So these two populations are independent of each other. These two samples are independent from each other. Okay. And in the first case, again, going back to the first case, two independent samples with known population standard deviation. Now, pay close attention here. This is population standard deviation, not sample standard deviation. So in this first case, we assume that sigma A and sigma B to be known, or the samples are large. Okay, so the size of each sample is higher than 30. Okay, which effectively enables us to assume that sigma is equal to S, because the sample size is so large that we can safely assume that sigma is equal to S, right? So this becomes a two-sample z-test, right? The second case is two independent samples with unknown sigmas, so we don't know the value of the population standard deviation, and the samples are small. Okay, so each of the sample size is less than 30. So this becomes a two-sample t-test. Okay, so as you analogous to one sample t-test, here you cannot assume sigma to be known, so you have to use S. You have to use the population standard deviation. Okay, you cannot assume sigma to be equivalent to S, right? And the third one are two samples in pair, so we call this pair t-test, or we call this last category is associated with paired data berpasangan. Now, this is an easy example. Okay, so this would be the minions. Okay, sample A, this is their usual state, and then sample B is their body weight after they do some sort of diet. Okay, and so what we do is we measure the body weights of Stuart, Bob, and Kevin before and after the treatment. Okay, before and after the diet. So in effect, we come up with a paired data. So each of these minion results in one pair of data, right? Their body weight before and after the diet. So we say that there's a correlation, there's a statistical correlation between members of population A and population B. So we call these two populations paired data, or not independent. Ya, jadi ini adalah data berpasangan. Data berpasangan itu biasanya lahir dari situasi di mana setiap anggota populasi itu dikenakan dua perlakuan yang berbeda. Ya. Dalam contoh saya ini sebelum dan sesudah diet. Ya. Sampel A ini sebelum diet, sampel B adalah sesudah diet. Nah, masing-masing anggota itu menghasilkan satu pasangan. Jadi Stuart ini diukur berat badannya sebelum dan sesudah diet, dia menghasilkan satu pasang data. Bob ini juga dihitung berat badannya sebelum dan sesudah diet, dia menghasilkan satu pasang data juga, dan seterusnya. Nah, secara keseluruhan, sampel A dan sampel B ini menjadi data berpasangan. Ya, dan ini metode ujinya berbeda dengan data yang independen. Okay. And here are the formulas. So these would be the formulae for the two sample test of the means. Ya, ini adalah rumus-rumus untuk uji hipotesis rata-rata berdasarkan dua sampel. Ya. First one, if the first one applies if the sample is large. Ya, perhatikan ukuran sampel tidak sama dengan jumlah sampel. Dalam kasus kita ini jumlah sampelnya ya 2. Okay. So please distinguish between number of samples and size of sample. In our case, the number of samples is always 2. We're comparing 2 samples, right? But the sample size might be any number that you can get. So in the first case, the sample size, ukuran sampelnya, is large. Large means the individual sample size is more than 30, larger than 30. Okay. Yeah. So clearly, if we compare to compare this to the previous picture, so you can see clearly that this is a small sample problem, right? Because each sample only consists of 3 individual plants. So n sub A is 3, 1, 2, 3, and n sub B is 1, 2, 3 as well. Okay. So clearly, this is not a large sample. Okay. Okay, two sample z-test, you can do this if the sample is large or if sigma A and sigma B can be assumed to be known. Ya, jadi kalian pakai rumusan untuk Z0 ini kalau N-nya besar, NA dan NB-nya masing-masing lebih besar dari 30, atau kita menganggap sigma A dan sigma B ini diketahui. Ya. Ingat, sigma A dan sigma B, bukan SA dan SB. Sigma adalah simpangan baku populasi. S adalah simpangan baku sampel. Oke. Ya, rumusnya ini adalah rumus untuk Z0. So this is the formula for the test statistic Z0. Okay. Z0, Z0. Yeah. That's your, this is the sample mean of A, this is the mean of sample B, that's the increment. Of course, again, if you test equality of mu N and mu B, then automatically delta 0 is set to be 0. Okay. And these are the population variances of A, and that's population variance of B. NA and NB are sample sizes of A and B. Okay. So the next one. This one here, 2 independent samples with unknown sigmas, and the sample sizes are small. For us in chemical engineering, perhaps this is a much more common case than the previous one. Okay, so in chemical engineering, we rarely work with large samples, especially if you're still in university. Now, if you're working in the industry, there are chances that you work with large samples, but if you do your, if you're doing your lab tech or your penelitian, your TA, then more often than not, you will end up with small sample problem. Okay, right? Now, for the small sample problem and with sigmas unknown, we have 2 subcases. So we have first subcase is where sigma A is equal to sigma B, and the second subcase is where the 2 standard deviations are not the same. Okay. Now, and each subcase have their own formulae. So, for example, for this one here, this is the formula to calculate the the test statistic. Okay, the T0. And S sub P is pool standard deviation. So this is some sort of an average standard deviation, and this is the formula. Of course, with the formula this long, I'm not asking you guys to remember this stuff, okay? But you really have to know which formula is appropriate for which situation, okay? Well, sometimes students got creative, so when they were given the exam problem, they did both. Okay. Jika sigma A dianggap sama dengan sigma B, hitungannya begini. Jika sigma A tidak sama dengan sigma B, hitungannya begini. Well, yeah, but you don't tell your faculty member to do the selection for you, right? Ya. Jadi ya kalian mahasiswa yang harus menentukan mana yang tepat gitu ya. Jangan dosen yang suruh milih. Pak silakan pilih mana jawaban yang benar, pasti salah satu benar ya, nah aja gitu ya. Ya itu pasti kami korting nilainya kalau begitu, gitu ya. So you guys have to know which formula is appropriate for your situation. Is it this one or even that one? Yeah. Okay. Now you may be. Oh, sorry. Let me go here first. So this one, this is a joint degree of freedom. Okay. So there's no subscript 1 or 2 in the Greek letter new here, but just new. So this means this is a joint degree of freedom, and this one is a joint variance. Okay, it's called pooled variance or pooled standard deviation. Di pool, jadi digabungkan. Yeah. Okay. All right. Any questions here? In an exam, usually, well, of course, it's most likely your exam will be open book anyway. So, but in years past, okay, meaning before the pandemic era, so we usually write down these formulae in the exam problem, so students don't have to remember this lengthy calculations. Okay, but we're not telling them which one works for which. Okay. So we might have just written this formula, and then students have to figure out, okay, which one applies to which situation. Okay, meaning we typically did not write this one here in the exam problem before the pandemic. So we're just blanking everything here. We just give you a bunch of formulae, and students have to know which one applies to which situation. Now, with the pandemic, of course, it's quite impossible to do that. So, actually, it gets a little bit easier for you guys because now you're doing this exam on an open book basis. But still, you really, really have to know which situation requires which formula. Okay. All right. Any questions here? Now, of course, when you're faced with this case, okay, when you're faced with the two independent samples with unknown sigmas, and the sample size are small, and you have to decide which one to use, whether it's subcase number 1 or subcase number 2, then to be sure, you can do which test first before you decide. If you're faced with having to make a decision, which one to use? Is it this one or this one? Is there any way that we can check this, in an elegant manner, in an accurate manner?
So can we just assume that sigma A is equal to sigma B initially?
No, you cannot do that. Well, you can, but you will get point reduction because that's not the correct way of doing it. What have we discussed in the first hour today? What test that we discussed in the previous hour from 7 p.m. to 8 p.m.?
Yang variance, sir?
Yeah. So in the first hour of this class, today, this morning, just now, okay, we have just discussed how to test equality of variance. So if you're faced with this case, then it is appropriate to do an F test first before you do the T test, because you have to know which T test applies. Is it this one or that one? You cannot simply just assume, okay, we assume that the variables are equal. Yeah, right. Okay, why don't you just perform an F test first to check that assumption, right? So it needs to be automatically built into your, to your work habits, okay, to your algorithm in our mind, when we are faced with this problem, okay, then we need to do an F-test first to make sure which subcase applies, right? Okay, so don't be like my students several years ago. The student gave me both. So if case one applies, then this is the result. If case two applies, then this is the result. Okay, well, you're not wrong 100%, but I gave the student a point reduction because he asked me to work. Because whether instead he should have done an F-test first to make sure which one applies. Oke. Ya, jadi jangan kalian pada saat ujian itu kalian coba semua. Kan nanti pasti ada yang pas gitu ya, cocok gitu. Wah, coba aja. Kadang-kadang bahkan saya dapat 3 loh. Jadi kadang-kadang mahasiswa itu mengerjakan 3-3-nya. Nah, terus gimana? Terus saya disuruh milih mana yang cocok, ya nggak bisa gitu ya. Oke. Because one of the most important point here is not being able to perform the mathematics, but you guys need to know which one applies to which situation. Yeah. Is the problem a big sample problem? Is the sigma known or not? Okay. If the samples are small and the sigmas are unknown, how to check if the sigma is equal or not? Then we need to perform an F-test first. Yeah. Okay. So make sure you do that when you're faced with this problem, this kind of problem. Okay. Ya, jadi ini saya ulangi dalam bahasa Indonesia supaya lebih jelas ya. Jadi jangan kalian mengerjakan permasalahan ini dengan cara coba-coba gitu ya. Coba rumus 1, rumus 2, rumus 3, nanti salah satu pasti berlaku. Ya iya sih, tapi nilainya saya kurangi karena itu artinya kalian tidak memahami persoalan ini sebetulnya cocoknya dengan rumus yang mana. Persoalan ini apa sebetulnya? Apakah ini persoalan sampel besar atau sampel kecil? Kalau sampel kecil, apakah sigmanya dianggap diketahui atau enggak? Ya. Kalau sigmanya pun juga tidak diketahui, apakah persoalan ini sigmanya equal atau enggak? Ya, artinya harus dicek dulu dengan F-test. Kalau ternyata hasil F-testnya menunjukkan bahwa sigmanya equal, maka kita larinya ke sini. Gunakan rumus yang ini. Kalau ternyata sigmanya tidak sama, maka kita larinya ke sini pakai rumus yang ini, gitu ya. Okay. So I hope that's clear enough. Okay. Now the last one is parity test, ya, uji T berpasangan. Okay. Ini pendekatannya sama sekali berbeda. So the approach that we'll take in this pairwise comparison, sorry, not pairwise comparison, parity test, okay, is totally different from what we use in independent samples. Okay, so what the key quantity that we're using here is the mean difference. Now, let me explain this by using an example. Okay, I think it's much easier for us if we talk using example. All right, so this is assume that we have 4 glasses, okay, containing water. Okay, pH standard water. Again, I do apologize. There's some mistakes in the translation. In my defense, I was the one who translated this. Sorry. Okay. Right. The original slide that I prepared was in Indonesian, and somebody else translated this. Okay, this is not standard water. That's standard solution, actually. There we go. Standard solution? Yeah, that's standard solution. Wait. Yeah, that seems to be water, I think. Water. There you go, specimens. Yep. Ah. I'll make sure I will upload the corrected version in EduNext. All right. Yep. Okay. So we have 4 classes containing water specimens, right? Now we have essentially these 4 classes are independent of each other. However, each class is measured. Okay, the pH of the water specimens in each class was measured by 2 different pH meters. Okay, so this is a pH meter brand A and this is brand B, right? And we want to see if there's any difference in performance between pH meter A and B. Ya, jadi ini ada 4 gelas diisi air. Kemudian setiap gelas ini pH-nya diukur dengan 2 alat yang berbeda, pH meter A dan pH meter B. Dan kita ingin melihat apakah ada bedanya nggak antara 2 merek pH meter ini. Ya, so each glass will result in a pair of data. Okay, for example, class number 1, okay, pH meter A results in a value of 6.1 and pH meter B results in a value of 5.7. And we define the difference to be A minus B, so left minus right. It doesn't matter. It doesn't matter if you're setting the differences as left minus right or right minus left. That doesn't matter as long as you do it consistently. Okay, either left minus right or right minus left. Do not take the absolute value, but you need to take the original value. Okay, so in this case, it is defined as left minus right. Okay, so it's 0.4, and then for class number 2, it's 0.2, right? Class number 3 is 0.3, and class number 4 is 0.3. Okay, so this will be the differences in readings between pH meter A and pH meter B, right? And then we take the average of these differences. Okay, so we take the average of these differences and we denote the number as d bar. Okay, so this is the mean difference, right? This is the mean difference that we obtain from our samples. Okay, so we simply take the mean of these numbers and we obtain 0.275. And lastly, we calculate the standard deviation of these differences. Okay, so these numbers, okay, we calculate the standard deviation of these numbers, and that is designated as S sub D here. Okay, this one. Right, now, having calculated these 2 numbers, we proceed with the hypothesis test. Okay, so the D bar is called the mean difference. Okay, and the value of D bar is compared with some reference value. Okay, and the reference value or comparison value is called mu sub D. Right. Of course, if your hypothesis, if you want to check the equality between A and B, ya, jadi kalau kalian ingin menguji apakah pH meter A dan B ini pembacaannya sama atau enggak, maka mu D, mu sub D ini diset dengan 0, diset sebagai 0. Bisa juga, ya, bisa juga kalian ingin menguji, misalkan kalian curiga nih, misalkan pH meter A itu pembacaannya konsistennya lebih tinggi daripada pH meter B. Okay? So in some instances, we want to prove if there's a consistently higher or lower observation within the means, within the pairs. So for example, here, if we just simply eyeball the numbers here, we can see that pH meter A tends to give a higher reading compared to B, right? So you might want, depending on what, again, this really depends on what you want to prove. For instance, you might want to prove that pH meter A consistently gives a reading, let's say like 0.3 point higher than B, for example. Then you can set this mu sub D to be 0.3. If that is that's the difference that you want to prove. Yeah. So again, going back to what you want to prove. Then the alternative hypothesis H sub 1 could be this one here, unequal or larger to or less than T0. Okay, and then this is the test statistic, the T0. Now, one thing that I want you guys to be careful about, okay, even though the random variable or the test statistic that you calculate have the same designation. Jadi meskipun namanya sama-sama T0, ya misalkan T0 di sini dengan T0 di sini, ini kan rumusnya lain. Ya. Jadi tergantung dari situasinya. Meskipun namanya sama-sama T0, tetapi rumus tergantung dari situasinya. Untuk data berpasangan, rumus T0-nya begini. Ya. Oh yes, and by the way, when it comes to paired t-test or paired data, we don't use paired z-test. So there's no such thing of paired z-test. We always use paired t-test. Okay. Jadi kalau datanya berpasangan, otomatis yang digunakan adalah uji T, di mana rumus T0-nya seperti begini. Ya. Okay, so this is the T0. Okay, the T0. T0 is the mean difference d bar minus comparison value mu sub d divided by the difference standard deviation divided by square root of n, where n is the number of pairs. So this is not the number of data points, but this is the number of pairs. In our case, on the left hand side here, n is equal to 4, not 8 but 4. Okay, and this one is the formula to calculate the degree of freedom. So the degree of freedom is the number of pairs minus 1. Yeah, again, in our case, on the right hand side, in our example, so nu is 4 minus 1 equals 3. So you can plug in the numbers for our example on the right hand side. So all you have to do is plug in all the numbers, then we get T0 equals, the D bar is 0.275, right? Minus the mu sub D in this case is set to be 0 because we want to test the equality of pH meter A and pH meter B, divided by S sub D. The S sub D is 0. The difference standard deviation is 0.096 divided by square root of 4. Okay, and then you'll obtain the T0. And the critical value, let's say if we work with alpha equals to 0.05, then and if we assume the test to be two-tailed, in this case, okay, let's say that we want to prove the equality, hence the test will be two-tailed, then the alpha is, of course, becomes alpha over 2. Okay, so this would be, if this is your T distribution, so we will have 2 rejection regions, right? So we have lower critical T and upper critical T. Okay. All right. Any questions? Next week we will have a tutorial session. So next week I will recap. We will recap the things that we have learned in inferential statistics. So the tutorial session will cover from module 5, okay, or confidence interval, and then module number 6 on one sample hypothesis test, and module number 7, which is two sample hypothesis test. Okay. All right. Any questions?
Could you repeat about the comparison value for mean difference? I'm still a bit confused.
The what again? Sorry, could you repeat that?
The comparison value for mean difference.
Comparison value for mean difference. Oh, okay, got it. This one here, right? Okay, now let's say that again, this is really what you want to prove. Okay, so if you want to prove that these two pitch meters, okay, they work equally, meaning they give identical readings, right? Then you set the mu d to be 0. Ya. Jadi kalau kita ingin menguji apakah pH meter A dan B ini sama pembacaannya, maka mu d ini menjadi 0. Okay, meaning, so this one, right? This becomes a d bar equals 0. Itu artinya sama saja dengan kita ingin membuktikan apakah merek A dan merek B ini menghasilkan pembacaan yang sama atau tidak ada perbedaan. Misalkan kalau kita kembali ke contoh minion tadi ya. Nah, jadi kalau misalkan ini mu d-nya ya, if I set the mu d equals to 0, then this implies that I want to challenge the claim that this diet reduce their weight. Okay. Jadi saya ingin men-challenge asumsi bahwa diet ini menurunkan berat badan. Jadi kalau mu d saya set 0, artinya diet ini tidak berpengaruh. Antara sampel A dan sampel B berat badannya sama aja. Itu kan ya. Jadi sampel treatment tidak berpengaruh. Itu kalau saya set mu d sama dengan 0. Nah, tapi misalkan, so for instance, I want to prove the claim that this diet can reduce these guys' body weight by 5 kilos, for example. Okay. So in that case, the mu d becomes 5. It's a non-zero number, right? So that's what mu d means. It means a specific difference between treatment A and treatment B. Yeah. If you want to test equality between, or in other words, if you want to challenge, if you want to test that, or if you want to confirm if the treatment does anything at all, then mu d is set to be 0. Yeah. But if you want to challenge the claim that this treatment results in some degree of difference, then the mu sub d will be non-zero. Nah, saya kasih contoh gini deh. Ini soal yang pernah saya keluarkan dulu di ujian kompre, wah udah lama sekali, bertahun-tahun yang lalu. Ya. Jadi ceritanya, Himatek ini bikin obat pinter. Ya. Yang mereka klaim kalau mahasiswa itu minum obat itu, maka nilai komprenya naik 20 poin. Ya. Oke. Dan kemudian dilakukan, ini sebetulnya contohnya mungkin nggak relevan amat, tapi ya saya rasa mudah untuk kalian mengerti lah. Jadi misalkan sekarang saya punya satu grup mahasiswa yang bersedia ngambil ujian kompre 2 kali. Ya. Pertama tanpa obat, dan kedua dengan obat. Ya. Kalau Himatek klaimnya adalah ini obat ini akan meningkatkan nilai kompre setidaknya 10 poin. Okay, so again, let me repeat this in English. So if Himatek claims that their magic potion, okay, can increase the score, the comprehensive exam score by at least 10 points, then what is the value of mu sub d?
Is it 10, sir?
Yep. So in that case, okay, in that easy verbal case, then the mu sub d will be 10. and the hypothesis statement will become like this. Okay, so the null hypothesis is new DGs. So just strike that. So the D bar is, am I doing this correctly? Yep. Okay. Got it. Wait. I think I made a philosophical error here. Anyway, that's okay. That's not too critical. The sample. Okay, so the null hypothesis will be D bar equals to 10, right? That's their claim. Sorry, they want to prove that the magic potion will increase the score of comprehensive exam by at least 10 points, right? So they claim that a D bar is higher than or equal to 10, right? So their original claim contains kesamaan, similarity statement. So their original claim becomes H0. And the H1 is, of course, the complement, which is D bar less than 10. Okay. Okay, anybody still not clear about what I just did? Okay, let me repeat this in a verbal statement, ya. Jadi Himatek mengklaim, ya, obat ajaib mereka akan meningkatkan nilai kompre setidaknya 10. Setidaknya 10. Ya. Dan ini kemudian mereka uji dengan sekelompok mahasiswa yang mengambil ujian komprenya 2 kali dengan dan tanpa obat. Ingat, orangnya sama, dikenai 2 perlakuan yang berbeda dengan dan tanpa obat. Jadi mereka ujian komprenya 2 kali. Oke. Nah, jadi klaim awal dari Matek adalah D bar, ya, D rata-rata itu lebih besar sama dengan 10. Ya toh, kan mereka klaimnya menaikkan setidaknya 10 poin. Jadi lebih besar sama dengan 10. Ya. Jika pernyataan Himatek ini salah, maka situasi yang akan menjadi benar adalah D bar ini komplemennya yaitu kurang dari 10. Ya. Nah, dari 2 pernyataan itu yang mengandung kesamaan yang mana? Yang mengandung kesamaan adalah klaim original dari Himatek. D bar lebih besar sama dengan 10. Maka itu menjadi H0. Ingat, tanda H0 tidak boleh lebih besar sama dengan, bolehnya hanya sama dengan saja. Jadi H0-nya D bar equals to 10. Dan H1-nya adalah pernyataan keduanya tadi, komplemennya tadi, D bar-nya kurang dari 10. Ya. Nah, so now let me twist this story a little bit, okay? This Himatek story a little bit. Now, of course, it is, of course, difficult for Himatek to find any volunteer that is willing to take compre exam twice, right? All of you guys will only want to take the compre exam once, I assume. Okay, so and the Himatek then is forced to perform to conduct the test using 2 groups of different students. So one group receive this magic potion, the other group does not receive the magic potion. Now let me ask you, is that situation the same as the one that we have just discussed a minute ago? Sama nggak dengan situasi yang sebelumnya?
I think it's different here.
What?
I think it's different.
Okay, in what sense?
Because the capability of the students are different. It's, it's not the same person. Somebody could be smarter, somebody might not have studied as much, so it's different.
Well, yeah, but the point is that one group receive medication, receive the magic potion, one group does not. And these 2 groups consist of different students. So what we have now are what kind of sample? Are they independent samples or paired samples? Remember, the students are different between group A and group B.
I think because it's different, it's independent.
Yes, because the sample members are different. Okay, the population members are different between sample A and sample B, between group A and group B. So now we're changing the situations into two independent samples. Okay. Now these things you have to be familiar with. Okay, so you have to be able to judge if what we're dealing with are two independent samples or two paired samples. Okay. All right. Okay, any questions? If not, I have to prepare for my trip to the campus. I need to do an offline meeting. Okay. We will have more time to discuss these details in next week. Because again, next week will be reserved for tutorials. So, oh yes, by the way, we need you guys to have well, I'm sure you already have Excel installed in your computer, but we just want to make sure. So make sure that you have Excel ready in your laptops because we will use Excel a lot next week. Okay. Right. Okay, if there isn't any question, thanks for your attendance and we'll see you next week. In the meantime, please do watch the videos that I have uploaded and be aware of that F-test, okay, because if you need to remember the lecture that we have today. So the example for F-test, the alpha should be half of that. So the alpha should be 0.025, not 0.05, because the original claim is two-sided. Okay, the original way that we set up the hypothesis is it should be a two-sided test, not one-sided test. Okay, so be especially careful with F-test. Okay, mathematically, the way we formulate F0 is such that an F-test is always a one-tailed test, but if the original claim calls for a two-sided H1, then when we look for the critical F value, the alpha should be halved. If originally it is a two-way test. Okay. All right. Thank you very much, and we'll see you next week. Take care and stay safe, stay healthy, all you guys. Okay.
Thank you, sir.
Yep.
Thank you.
Thank you,
Thank you,
sir.
sir.
Thank you,
Thank you,
sir.
sir.
Yes, sir.
In case you're curious, we don't have any announcement yet from ITP about when you guys will be asked or will be allowed to come to the campus. Probably you guys are, well, we prioritize several lab courses, of course. We prioritize lab tech. I'm not really sure about MPA. Has it been prioritized yet? My guess is not yet, but in any case, just keep your eyes open, keep your ears sharp for any last minute changes, okay? Because the situation is not settled yet. So the situation is very dynamic. It could change on a weekly or even daily basis, perhaps. Okay. Right. So I think if you just keep an open communication with the program, with Kaprodi, with your friends, with your docent wali, should be okay. Okay. All right. Thank you very much. See you next week.
Thank you, sir.
Yep.